problem is that I think the right question at this stage and in this course is not, we're not going through a rigorous proof and anything. And if you're math majors, which majority of you are, there's of course something called advanced calculus, and you approach this type of thing a lot more rigorously than in here. But I still like to ask a good question in here, so which is this okay? Let there be a number I, and when to consider this one multiply by real number and add by real number, which is what you did, right? You just practice, assuming that everything is okay, right? And probably the very first concern when people are dealing with this number is probably this question: is this okay? So what is this question exactly asking? Is that, will there be someday some sort of contradiction? For example, if you did lots of algebra, some crazy algebra went through, you end up at 0 equals 1. It's not good, right? That's what we mean by contradiction. So that's the question. Is this okay? Okay, so let me address that. Right now, this course in algebra, abstract algebra is going on. Abstract algebra is offered every fall. And in that course, you have very nice algebraic construction when you enter rings and modules, and toward the end of this abstract algebra, they give you very good construction. That's a lot of work. If you have taken number theory type of course, you have an idea about the modulo structure. That's how they entered. I realize it. My favorite world already has this answer to that one, so I'm approaching to that one. I'm going to show you this is okay, and hopefully you're going to believe this. All right. So here's my approach. First, let me go through this the better construction. So here's the idea. If this is okay, and what we do here is enlarging the real number. That boldface R is real number, and we include that. We don't hurt that, and throw in one more numbers, and we enlarge it by adjoining number I. By the process adding and subtracting and multiplying. Let's not think about dividing yet. Okay? So we know how to multiply I and I, and we of course extend natural distribution laws, associativity law, and distribution law, commutative law, all the property that we enjoy when we do algebra, right? And things we just extend that, and add this real number 2i and multiply real number 2i, I to itself. You do all sorts of things, and will there be a contradiction? That's what I'm asking here. All right. So here's a world where you will see this one is happening, and because this world is something you already know, so you accept everything that's happening inside this world, there's no contradiction. So that world is this M-mat2R. Do you know what that is? I'm going to describe it as a set. The space of 2 by 2 matrices. Okay? 2 by 2 matrices. It looks like this A, B, C, D. I'm going to use bracket instead of parentheses. And these number A, B, C, D are all real numbers. Okay? All right. So you know these matrices, right? We all have encountered matrices before. This is introduced as a function. This full number becomes a function. This is a function from xy plane, which is denoted by R2, okay, or R cross R. One real number x, another real number y. All combination is denoted like this. If you have xy plane, if you hit that point xy by this matrix from the left, so 2 by 2 matrix multiplied by column vector of size 2, you get column vector of size 2 again. So each of the points, if you hit it from the left by this matrix, you get another point, right? This map is called linear transformation on R2. So those linear transformation is described by this full number. So although we abbreviate it like this, what this really is a name of a function that involves, parameters like that. So what we can do with this function is that we can add these two functions. I'm going to call this matrix A, matrix B. if they're all coming from this matrix 2 by 2 matrix space. Make sense? If I have two matrices, I can add those matrices. Each entries is add up. Okay? Make sense? And subtraction, obviously. This A times B, this matrix, has a special meaning. I'm sure you know how to do this. But I'm going to write A2, 1, 2, 3, 4, and 5, 6, 7, 8. How about that? You have two matrices multiplied together. In terms of function, I identified each of these four numbers as a single function on xy plane to xy plane, right? So the meaning of this multiplication of these two matrices in terms of function, does anybody know? This multiplication of the two matrices represent what of the two linear transformation of this and that? What is that word what? This is a matrix multiplication, but it represents something called composition. Do you know what a composition is? We have two functions. You stick in one function, you get the output. That output goes to the next function. That's the composition, right? So if you compose a two function, what's going to happen to the linear transformation? Is there a quick way to figure out that linear transformation in terms of matrix again? And that's what this matrix multiplication is. So how do you do that? You multiply 5, 7, cross it down, right? So is that 5 plus 14? Is that right? And you multiply 5, 7 there. Is it 15 times 28? That makes the first column of that. And 6 plus 16 and 18 plus 32. Those, if you simplify those are the four numbers. So if you compose these two transformation, it becomes this single linear transformation. Matrix multiplication is a short and a quick way of calculating composition of a two linear transformation. Make sense? So if we have these four numbers and one entity in that, you can add and subtract and multiply, right? And I hope you believe there's no contradiction in this world. Okay? So there's no contradiction. If I can discover what we want to discover in here, then we are in that situation. We're okay. Okay? That's where it's heading. And that's what they're doing in here. Abstract algebra is more convoluted though. It's a lot straightforward in here. Okay, these are the numbers in there. So what I'm going to do next is I'm going to discover a copy of R. What's R? R is the real numbers, right? Each thing in there is not real number. These are matrices. It's like a full real number put together. So I'm going to define subset that are coming from there. This off-diagonal terms are zeros. And I'm going to put x in here. And x is real numbers. I use the term subset. Does this one look like a subset of the 2 by 2 matrices? It's coming from 2 by 2 matrices. I put some restriction to each of these entries. This off diagonal is in 0 and 0, and diagonal terms are exactly the same. Okay? Now we can add and subtract and multiply all these things, right? So I'd like to claim that this one behave just like real numbers. So let me say that again. In terms of addition and subtraction and multiplication, these matrices behave just like the real numbers. If I'm looking at this particular matrices, and if you want to compare how this one behaves like an R, what would be the good choice of R, real number that correspond to that one, is X. X is a real number, but what you do with that real number is you create this matrix, X0, 0x. Okay? It's a matrix, but in terms of arithmetically, they behave really just like X. So for example, if I have, so I'm going to describe this correspondence like this. Okay, if I have a number X, I'm going to create 2 by 2 diagonal matrix. That map is going to be denoted here in Mathematica. Also, it's going to be psi. I think it is spelled like this. Hope I'm pronouncing this correctly. It's a Greek letter, psi, the capital. All right. So if I have x, what is the matrix going to correspond to? X0, the diagonal matrix with that same entries there, right? Okay. So that's what that is. So if I have two things, R cross R. Do you know what that is, R cross R? XY plane. Two number, x comma y. And that's going to go to V cross V. So if I have x comma y, and we're going to add and subtract and multiply. How many operations? 3 operations, right? So I'm going to abbreviate like this. We're looking at 3 different operations in the vertical. If I have 2 numbers, I'm going to add and multiply and divide like that. If I have 2 matrices here, we do the same operations and come up with that same 2 by 2 matrix again. And we're going to compare this one in here. I have 2 numbers, x comma y, which is a real number, and you go to this matrix, x is 0, 0 there, y 0, 0, y. Those are the 2 corresponding matrices there, and we do same operation there. Okay. For example, we're going to do x plus y, right? We're going to do x minus y. We're going to do x times y. Those are the 3 operations we're going to compare. Let's do that with the matrix too. I have these 2 things. We're going to add these 2 matrices. What are you going to get? X plus y, y plus x plus y, 0. If you add those 2, don't you get this matrix, right? Each entry is added. And if you subtract those 2 matrices, you get x minus y diagonally. Let's multiply carefully. So who wants to go for a multiplication? 0y here, that column is multiplied to the row, right? So what is it? You get xy plus 0, is that right? That column is multiplied to the second row, dot product. Remember dot product? So each entry is multiplied, so you get 0 plus 0, right? Second row is multiplied to, second column is multiplied to row if you multiply it. So you see 0 plus 0? If you multiply that second column to the second row, you get 0 plus xy. Okay? So let me explain what just happened. We started with this pair of numbers, and then we sent it to the matrix world and went through operations. And we took that pair of number and we did the usual operation down there. So we went through 3 different ways, right? Now I'm comparing the resulting things, x plus y. Under the psi map, x plus y does really go to x plus y, right? X minus y does really go to x minus y. And x times y really goes to xy there, 0, 0. So although we went through 2 different paths, the bottom correspondence agree with what map? Psi map, right? I didn't calculate a psi map here. I just compared what happened. It happened to agree with the psi map. Okay? Therefore, this dotted line can be just solid line in the psi map. If this happened, everything else you calculated and the remaining thing checks with what you expect, then it becomes something called commutative diagram. All right? So, let me go back in here and say the way the V behaves arithmetically is just like real numbers. Does that kind of make sense? So V is a copy of R. V involves only one parameter, therefore it kind of corresponds to real number. The way they add and subtract and multiply is exactly the same. Even division is going to be the same, which I didn't do in here. All right? So would you believe we found a copy of R in disguised form? It has different shape and name, but behaves just like R. Good? Right. So what we have to find is imaginary number I in there. Okay? Imaginary number. So I'm going to call that matrix. Let's find matrix E, A, B, C, D. We want to find that matrix, right? So what determines the imaginary number? Such that, how did we define imaginary number? A number whose square is -1. But inside the matrix, what is the version of -1 here? -1 is a real number, right? How did we find the copy of real number inside? This was a copy of a real number, right? Diagonal term being same. So what's the diagonal term here? -1. This one corresponds to -1, and they behave exactly like a -1 in the real number. So can I go ahead and multiply this A, B, C, D to itself, and then figure out -1 and so on, and come up with some A, B, C, D, right? So I'm going to write down one answer, but there are infinitely many full numbers to that one. I think is a good time to introduce how to do this in a Mathematica rather than explaining. Okay. So that will be square of this matrix. That you can do by hand, but you can do this quickly like this. Okay? And you want to set this one equal to what? -1, 0, 0, -1. And you look for 4 numbers that matches it. It turns out there are infinitely many of them. Okay? So we do that search in Mathematica, and we got this. I kind of chose the simplest thing, which is 1, 2, -1, and -1. Okay. If you actually try multiply to yourself, you can easily verify that's -1, 0, 0, -1. Okay? So this is a matrix whose square behaves just like -1, a real number, right? So let's do the same thing. That was V, the copy of real number. I'm going to extend it in the W. That A and B are coming from V. You know what that means? A and B are 2 by 2 matrices, but it looks like V. XX diagonal 0, 0. Right? So how do you create the imaginary, the complex number in here? A is a real number, behaves just like a real number, right? B is going to be another real number in front of imaginary number. What is the name of imaginary number inside this matrix? E we found. Okay? That's the matrix algebra. So if you look at this guy, W, that behaves exactly like what kind of number? Complex number. Okay? A is a real number and B is a real number. E behaves just like a number squared is -1. It's all happening in something we already know. There's no contradiction. So this guarantees that it's going to be okay because it's happening inside the matrix. Actually, all the